In this video, I'm going to introduce you to a new distribution called the T distribution. We use the T distribution when we are trying to estimate our population information from a sample, but we don't have information about that population, such as the population's mean or the population's standard deviation. So if we're missing sigma and we can't compute the standard error, what we need to do is use the properties of the sample, which are x bar and s, to estimate or assume our numbers for the population. This distribution is very similar to our standard normal distribution. It has the same bell shape. It has a symmetry. It behaves just like the normal in the sense that we can center it here at 0. We can use standard deviation type units to see how far away we are from the mean, and we can put probability and area and percentages in it as well. So what we can notice, though, looking at this diagram, the difference between the normal distribution, which is the solid line here at the top, and the T distribution. Now, the T distribution is affected by sample size. As we have different sample sizes, the shape of it is going to change. And when I say shape, I don't mean it's going to go from a curve to two bimodal humps. What I mean is that the area under the tails out here on the edges is going to change, and also the extent to which how high and how peaked it gets is going to change. So let me show you a simulation. Let me end the slideshow. This is a simulation of a T distribution where I can vary the size of the number of the sample. The number in the sample is represented by what's known as a degree of freedom. I'll talk about that a little bit more in a minute. But let's say with 1 degree of freedom, that means our sample size is 2. Pay attention down here to this blue dotted line, because that's our T distribution. And what we'll see is as we increase the number of degrees of freedom, that this curve acts as if it's no longer being pushed down. That's how I like to think about this. It's being weighed down by its lack of sample size. So as we do a higher sample size, what we'll notice first of all is that the peak will come up from the blue line to the maroon line, and we'll also pay attention to what's happening out here in the tails. These tails, which have a little bit of area in them, they're going to shrink down. So 2, 5, 6, 7, 8, 9, 10, 11, 12, 13, 15. So here's our sample size of 20, but we can still see that there's more area in the tails. It's slightly higher here. It's slightly lower. And as we keep increasing, it's going to take a little while for that difference to completely disappear. It's getting closer and closer, but again, we can still see that the blue line out here in the tails is higher. And now that I've cranked this all the way up, we can see that it's perfectly aligned. So the T distribution with a high number of observations in the sample will appear to be a normal distribution. And that's great for us, since we've spent so much time learning about the normal distribution, that in practice the T distribution is not going to be very different. Let's do an example. Here's a question from the text. Do students perceive themselves to be invulnerable? It's known that in the U.S. people typically die at age 75. A sample of 17 students were asked to predict when they themselves would die. Their scores averaged 84 with a standard deviation of 8.01. Do students believe that they will live longer than the national average? We're going to sort of treat 75 as a mu. But we have no idea about the spread of the population, right? We have no idea of what sigma is. This works pretty much the same way. Null hypothesis and alternative hypothesis. Again, I like stating the null hypothesis of whether or not our sample average is the same as our population average. And the alternative hypothesis is that they're different. The next step, we have to make a decision rule about our null hypothesis. Now typically, if we're doing a normal distribution and we say that with a z-score we want to have a 95% in the middle or 0.05 in the tails, we've sort of memorized this to be 1.96. That's our value of z that is going to give us these levels. For the t-distribution, we actually have to do something slightly different because, again, the shape of the t-distribution depends upon the sample size. To incorporate the sample size into our distribution, we rely on what's known as degrees of freedom. Essentially what we're doing is we're saying these degrees of freedom can vary while we hold one of them constant. Again, for me, mostly this is mechanical. If I have n number of observations for a simple question like this, I'm just going to subtract 1. So degrees of freedom equals n minus 1. And I need that degrees of freedom because I need to, again, incorporate the sample size and see what is my critical value going to be. So I've got a normal shaped curve. Even though it's a T, it's still bell-shaped. And to test my hypothesis to see if my sample is very much different from my population, I'm going to establish a region of rejection and a non-rejection. So here we would do not reject the null hypothesis. And if we're in these zones, then our sample is really different. The number that we can see down here at the bottom is not 1.96. It is 2.120. We get this number from our t-table. And so I'm going to talk to you for a minute about the t-table and how to read it. This one works just slightly differently from the standard normal distribution. With the t-distribution, if we look at the picture, we're still selecting the area that's in the curve. And we have to remember that if we're doing a two-tailed test, that we have to double the amount of area under the curve. So typically with our 95% confidence intervals, we are doing curves that have 0.05 in the tails. Well, when you divide that by 2 tails, 0.025. So this is the column that we are going to use the most. So we've selected the t for 0.025, which again, when you double it, gives us 0.05. That's for our alpha. We read the column by first selecting the number of degrees of freedom. Now our example before, our n was 17. Degrees of freedom is n minus 1, so 17 minus 1 is 16. And I couldn't get it to fit on this slide, but if you look at your printed out copy, you'll get a value for t. And so what we do is we go across and we find the value for t, and this becomes the critical value for t that we place on our little diagram. So as the degrees of freedom changes, our number for t is going to change. So that's how you read one of these tables. So doing that for this example, t with 16 degrees of freedom is 2.120. So we, on both the positive and on the negative side, if our t-value that we compute given our data is greater than that, then we will reject the null hypothesis. The t-statistic is generated the same way. We use our sample mean minus the population mean, and for our measure of variance, we're going to use standard error again. So this is the standard error of our sample means. We're going to compute that S of x bar by taking the S that we're given and dividing that by the square root of n minus 1. Now remember, you turn your phone sideways and you get the square root button on your calculator app. So our standard error is S, which was 8.01 in this example, divided by the square root of 17, and our standard error is 1.94. We're going to use that in our calculations to derive at t. Remember, our sample said that young people thought they were going to die at 84. We expect the population mean to be 75. With a standard error of 1.94, that gives us a t-value of 4.63. 4.63 is way out here in the tails. Way out in the tails. It's further than both 95% and 99% confidence. Okay, so it's really far out there. So we're going to reject the null hypothesis. The average estimated age of death for 17 class members was significantly greater than a population average of 75 years. Let's call this the optimism class. These people think they're going to live a long time. So for our t-test, again, we're using a sample, but there's an assumption that this sampling is random, that we're not picking based upon a particular requirement or potentially independent or controlling variable. We're also assuming normality. We're assuming that the data really should be normally distributed if we had a large number. Again, it's a fairly safe assumption to make. Lots of things in the population are normally distributed, but even if it's not normally distributed, the t-test is pretty robust, which means it's flexible enough that it will, even if we're not really supposed to be normal, we're going to get a good enough answer. And finally, interval or ratio level data. Again, let's just think of these as numbers that range. In other words, they're not really categorical, like they're not nominal, and they're really not ordinal either. We get into a lot of trouble with treating ordinal data as if it were interval level data. The biggest thing here is that we're using a t-test when we have a sample and we're not sure about how our population is distributed. For the biggest thing about the t-distribution is sample size. The bigger our sample size, the greater the probability of rejecting the null hypothesis. So when we're dealing with these sorts of questions, we want a large sample size. Now that goes against the whole reason that the t-distribution was created. The t-distribution was created by a worker of Guinness Brewery, and the folks at Guinness wanted to do quality control testing of their product. They wanted to make sure that their beer tasted good, but they didn't want to test all of their beer. So they wanted to find out under what conditions would a low number in their sample yield pretty similar results to a large N sample. So the way that the t-distribution is set up is that the larger the sample size, the closer we're going to approximate that normal distribution. So we have to be comfortable with figuring out, okay, how big should the sample size be? Ideally, it's as large as possible. So if we're given a survey, we're not going to stop asking people questions once we hit a certain number. We want it to be as large as possible. We're going to hopefully get as many respondents as possible. But when you're Guinness and you're deciding how much of your beer to waste through product control testing, that's less beer that you can sell. So here's an example where by changing the sample size, we can see how it affects the standard error. So with a sample size of 20, when you're computing the standard error, you get a t-score of 3.19. Same setup, but with a sample size of 10, you get a t-score of 2.25. This is much closer to do not reject area, and this is much further in the rejection zone. There's also a good time to talk about the idea of setting alpha. Again, for us, I always want alpha to be set in that 95 or 0.05 category. That's what we do in social sciences. You could set it to have a more stringent test, right? You could say that you want 99% in the middle, or just 1% in the tails. Some of the examples in the book and some of the questions use 90%. That's just way too easy for us, because what we're doing is we're putting more areas in the tail if we use 90% in the middle, and you can see that there's quite a bit of difference in the rejection number between 90 and 95%. One more thing to talk about with the t-distribution and hypothesis testing. We still have the option to do directional tests. So if your theory says that really the only outcome should be that your sample is higher than the population mean, and you don't want to include the possibility of it being lower than the population mean, you can take that 5% and pack it all in one tail. Now when you do that, though, you have to remember you're basically making it easier to reject the null hypothesis. So your audience of other scholars in this area are going to be a little bit more skeptical of your results, because they're going to be wondering why you went ahead and just did a one-direction test, and why you did a one-tailed test instead of a two-tailed test, which is the norm for social science. So what we have with the z-test and now our t-test is we can look at the difference between a sample mean and a population mean. With the z-test, we need to have those population parameters of mu and sigma. With the t-test, we're going to use our sample parameters, if need be, to simulate the population. And that's it for the t-test. Very similar to the z-score. I understand that we've got a new table, and so you need to keep a copy of this around. Remember that what we're doing with the t-table is we are using the area under the curve as a given and saying how much we want to put in the tails of the curve. The last thing I want to show you is that when we look at the bottom of this t-table, we can see that in fact it does get to normality, right? It does get to 1.96. Granted, that says infinity, but if we look at the numbers here, our t is approaching 1.96 the higher and higher we get. Some tables go up to about 100 or so. I'm not going to stress how close we get. Anything above, you'll notice, anything really above, let's say 28 or so, we're fairly close to that 1.96 in this area. This table will be good enough for our homework, and if we were really doing a test where we're doing research based off of these results, quite frankly, we're going to let the computer generate these t-values for us. It'll do that automatically in our statistical programs. All right, with that, that's a very quick introduction to the t-distribution. You should be good to go to do some homework.